Okay, so you had to go to a few exercises last night, did you?
Yeah. So we are going first.
Yeah, well, we'll have a look at what you did. Did you have any problems? Anything you didn't understand?
I had some problems with the exercises you told me not to do.
Oh, okay.
So yeah,
fine.
if we have time
Yeah.
later, maybe. I just wanted. I can show
it's
you
worth,
what I
it's
did.
worth doing them now so that we make sure you understand things.
So the one was page 30. Yeah, this one, but I think I forgot the letter from the paper where I did it. I will do it again. I took it until one point, and it was like this, for example, like the examples we did, and I didn't know how to continue it. But I forgot the other one where I had it. Anyway, let's start with what I hadn't.
So this one you could actually prove using the results we already have. So because we proved this, right? So if you know that, could you? No, sorry, that doesn't work. Ignore me. That doesn't work. No. Okay, that what I said doesn't work. I guess you have to do it.
Yeah, I will do it again. Yeah.
Um,
So the other one was this, which I didn't know how to do it at all, with the sandwich theorem.
For that one you just showed me, it might help to convert it into a partial fraction. Do you know what a partial fraction is?
No.
So what was it? It was n squared. Right here. It was n squared minus 1 over n squared plus 1. Is that right?
No, not this one.
Oh, for one you just showed me.
The previous one?
Yeah.
Or the wait.
For previous one.
Yes.
Yeah.
Let me have a look. Yes. Yeah, this is
So
equals. Yeah, but the limit of this
yeah. So
is equal with 1.
No, I don't think you don't have to.
You don't take the absolute of this fraction minus 1.
Yeah, exactly. And then what was the next thing you tried to do?
I just continue to do all the calculations inside.
But what was your next calculation?
So n square minus 1, n square plus 1 minus n square plus 1, yeah.
Yeah. So n squared minus 1 minus
n
squared plus 1.
Yeah. Yes.
So the n squareds cancel out.
Yeah.
And what you have minus, so that's a minus, so you've got minus 2. So this is minus 1, so this is the same as then 2 over n squared plus 1.
Yes.
You got to there.
So now we have to care about the fraction 1 over n squared plus 1, right?
Yeah, you can put a 2 outside if you want, yeah. 1. But so what you need to do is you need to bound this, right? You want this to be less than epsilon.
Yes.
So for that to be less than epsilon, or you can kind of do it directly. So 1 over n squared plus 1 is less than. So this is true if and only if. We're kind of working backwards. If that is less than epsilon over 2, n is positive. So this is all positive, so you don't actually need the absolute value things. So this is true if and only if you invert both sides, right? So n squared plus 1 must be greater than epsilon over 2. So subtract 1 from both sides. n squared is greater, so n is greater than the square root of epsilon.
Okay, so this is the solution.
So as long as n is, so you take capital N to be this, or this plus 1, then for n bigger than capital N, yeah, this will be satisfied, this will be less than epsilon.
Okay.
Does that make sense?
Yeah, I was trying to do it, a different, okay.
What was the other one you started?
The sandwich theorem is 36, yeah, this one.
Okay, so let me go to that slide. What page was it? 36?
36, yes.
So the claim is that square root n plus 1 minus square root n goes to 0. And what was this for sandwich theorem? What did it state? So you've got, what was it?
The sandwich theorem.
Yeah, it was yt less or equal to xt less or equal to zt.
Zn, yeah.
It was that one.
Yes.
And this is converging to L.
Yes. So
Yt goes to L, zt goes to L, and then
HD.
I'm using T, aren't I? Why am I using then? Stay consistent. And that implies that
H
xn
yeah,
goes
goes to no 12, right?
Oh, 12, yeah.
Oh, okay.
God, I'm very tired. Okay, so we want to bound this. So we think this is going, this is going to 0. So we want something that's. Does it give a hint with it?
No.
Give a hint for what we might want to bound it by. So what did you try? Did you have any
No, I
ideas?
didn't.
So we need something that's always bigger than this. Okay, so I'm guessing it's something to do with this. So what happens when we square that? You know, we've got a load of square roots, so squaring is a natural thing to do.
Yeah, okay, so this will be
You get that bit, and you get minus 2. I don't know if this is gonna work, but no. Oops. So
yeah.
this, yeah, we made a mistake. So this is 2n plus 1 minus 2 times square root n plus 1. Is there an obvious sandwich here? So, you know, if you look at this, here inside this square root we've got n squared plus n. So the square root is kind of going to cancel that bit out eventually. Let's just flick to the answers and let's see what they do in the answers.
Hmm?
There are answers in the back of the book,
okay.
so maybe that's the let's give us a pen.
this is 36. Okay, so we need 3.
Okay, so we're doing something simple. So it's for things squared divided by the thing. Seems it's a funny trick if you.
So
So maybe if
it's
you'd
0
seen
and
this trick before, then. Oh, it's always yeah. N plus 1 minus n. How do they get from there to there?
I think they divided.
No, so the bottom's staying the same. So all we've done is multiplied out the brackets like we did. So they have the 2n plus 1. Well, that's a typo, isn't it? They like drawing in books, but that's a typo. That's mistaken the answers. Okay, so let's follow their route. So we were doing the right thing. So this thing squared is this, and this is less than 2n plus 1.
Yeah.
Okay. So what we had to start with, so root n plus 1 minus root n, well that's equal to a lot of, in maths to prove things, you know, it often seems magical how you work out what trick you need in order to get there, and once you've seen it it's kind of obvious, but sometimes you can stare at a problem for hours and not see. You know, it's just the more problems you do, the more of these tricks you learn. I guess it's a long time since I saw this kind of things. So this is, all we've done is written what we started with as what we started with squared divided by what we started with. I'm sure there are other ways you could do this. So we've already proved that this squared is less than 2n plus 1. So this is less than 2n plus 1 over root n plus 1 minus root n. Okay. So again, we want to make that bigger or that smaller. Well, let's divide through. So 2n plus 1 is certainly less than 3n. I'm completely sure if this is right. So we're making 1 bigger. Okay, so we can. So this is less than 3n over what we had before. And then let's divide top and bottom by n. So this is 3 times 1 over n root n plus 1 minus 1 over n root n. Well, 1 over n root n is 1 over root n. So you can put if you like, you can put the n into the square root. So as you take the n from outside the square root to inside, it becomes n squared. Okay, so this is 3 square root n plus 1 over n squared minus square root n over n squared. Where did they go next? Let's look where. Got their rare ones there, haven't they? Exercises from 20. Let me just go straight to whatever we're doing. See exercise 4.62. So maybe it was easy if we'd done the previous exercises. Where is it? 4.62. So the claim according to the answers is that this thing is less than 1 over root n. So well, let's see if we can prove that. So clearly the answers think that's obvious. It's not obvious to me. So this thing, I put a question mark above it, so we don't know whether it's true. That's true if and only if 2n plus 1 is less than, if we multiply both sides by this thing. So this is definitely positive, right? Because n plus 1 is bigger than n, so this is definitely positive. Root n plus 1 minus root n over root n, which is true if and only if, and let's take root n back to the other side, so there's a 2n root n plus root n is less than 1 minus root n. They didn't do what I did. I can't read. No wonder this wasn't working. Okay, so let's start again. So what the answers did was this. So in what I'd written before, we had a minus sign there and a minus sign there. What they did, Yeah, so yeah, I suppose this is, you know, I can see why this is going to work, because you're going to get, when you multiply it out, you're now going to get a negative n term, whereas before you were getting a positive n term, it was causing us problems. So when you multiply out this top bit, you know, the answer's working out. This is giving you n plus 1, so then we get the interaction terms are going to cancel out, so we get minus root n plus 1, plus root n plus 1, so they cancel out, so we get n plus 1 minus n, which is why it was equals, why there wasn't a typo in the book, I'm sorry, and the bottom is still the same as what it was. So this is n plus 1 minus n, okay, so this is just 1 over root n plus 1 plus root n. And, well, we want to make this whole thing bigger, so we either make the top bigger or we make the bottom smaller. Okay, one way to make the bottom smaller is just to completely ignore that term. So it's certainly less than 1 over root n. So that was it. Sorry,
So this is the sandwich theorem. You just
so we know that naught is less or equal to this.
yeah.
Okay, the constant sequence of noughts certainly converges to naught. So a sequence where every term of a sequence is naught certainly so that bit converges to naught. This bit, well, we've never shown that converges to naught. You could show it directly, or you could use results we've already proven. So remember we proved that you can show it directly, but by 1 over root n minus naught is less than epsilon. Well, that's true providing that 1 over root n is less than epsilon. So root n is greater than epsilon, so n is greater than epsilon squared. You know, so as long as n is greater than epsilon squared, this thing will be less than epsilon. Okay, so you can prove separately that this thing converges to naught. It's kind of obvious that this converges to naught, right? 1 over root n. So I don't think the question expected you to prove that. But that bit goes to naught. Okay, so we've got that this expression is bounded between something that goes to naught and something that goes to naught. So it too must go to naught. That was the idea. Sorry, it took a long time to. Was there anything else you looked at?
Yeah. Just one moment. Okay. Yeah, so the next one, what they have done. Yeah, I did them. I think they are fine. They are okay. I don't know if you want to have a look. Yeah. It was 1 and 2. Something else I wanted to ask you, now that I said that. Do we put greater equal or just greater? Because in the book it's just greater.
It doesn't matter.
Oh, okay.
You know, if it's true, if it was true with this n with greater or equal to, then it's certainly also true with greater than.
Yes,
And if it's
yeah,
true, and if it's true with some big N with greater than, if you kind of increase big M by 1, then it's true with greater or equal to. So it doesn't matter.
Okay.
Some people use greater and some people
Okay.
use greater or equal to. It's the same thing. Yeah, that's fine. So okay. Oh, this is that version of a triangle inequality that we showed. Yeah. Yeah, and you're done. That was what we showed. What was that anyway? Yeah. And 2 is with this an answer for any xn greater than half the L. Okay, so you take epsilon is half L. Yeah, exactly. Yeah. That's good. Okay, was there anything else you wanted to?
No, I think this is it. Yeah, this is it. Yes.
Okay. Okay. Well, let's carry on from where we were up to then. So we're just about to start chapter 5, I think. So one thing that turns out to be quite important are subsequences. So if you've got one sequence that's, maybe you got the sequence 1, minus 1, 1, minus 1, 1, minus 1. We can take a subsequence by just picking some elements from this sequence. So I could take a sequence of these elements, all the 1s, 1, 1, 1. That's going to be a subsequence. So if xn is some sequence, so xn is some sequence of real numbers, and suppose n r, is that the notation they use? That's a sequence of natural numbers, okay, and it's strictly increasing, so nr, r in n, and we have that for all r in n, nr is in n, and nr is less or strictly less than 1 plus 1. Okay, so nr is a sequence of natural numbers. So for all elements of a sequence, nr is a natural number, and nr is strictly less than nr plus 1. Okay, so the sequence is strictly increasing. We've got some normal sequence xn of reals, then the sequence xnr is a subsequence. Okay, so suppose that xn was, I don't know, could be a sequence 1, half, a third, a quarter, a fifth. Okay, there's one sequence. And think about the subs. So we take nr to be 0, 1, 2, 4, 8, 16, etc. Okay, then x of nr is, the first element of this is given, so we look at nr says 0, that means the first element of xn, so the first element is 1, We look at nr, nr says 1, that's the second element of xn, so that's a half. Okay, we look at nr, nr says 2, so we take the third element. Okay, is this right? So this is like so if you like, this we're calling this the naughth element. This is the first element. This is the second element. This is the third element. This is the fourth element. Maybe it's easier if I start my sequences from. Let's number from 1 because it's easier for now. So let's go like this: 1, 2, 3, 4, 5. This isn't a very good example, is it? So if we number like this, the way the book does, 1, 2, 3, 4, 5, rather than starting from 0, and we take this subsequence, the element at 1, 2, 4, 8, 16, etc., then we get 1, a half, a quarter, 1 eighth, 1 16, etc. You see what we're doing? So the first element of this sequence, we look at this sequence, this says take element 1, and we take element 1 from that sequence. Second element of this sequence, when we look at the second element of nr, this says take element 2, so we take that one. The third element of this sequence, we look at the third element of nr, this says take element 4, so we take that one.
Okay.
Yeah. You know, so if you like, it's like composing two functions. Okay, so there we had xn equals 1 over n. I suppose x naught would have been infinity, wouldn't it? And then we had nr was 2 to the power of r. So x of nr is 1 over 2 to the power of r. So all we've done is, okay, I've done 2 steps. So xnr is 1 over nr, just evaluating x of this element nr. So
Okay.
So if you like, you can think of that this is a function. Okay, sequences are functions that map from the integers to the real line. Okay, so here we're kind of evaluating x of this value n sub r. Okay, so x of n sub r is 1 over n sub r. Okay, so, and we know that n sub r is 2 to the power of r, so this is 1 over 2 to the power of r.
Okay.
Okay, or 2 to the 1 over r. Which is, so it's the same example as what we just saw. Yeah, so there are a few examples here. Maybe these are clearer. I don't know. So if we've got some original sequence xn, one subsequence of xn is, rather than starting at 0 or 1, we can start at 2 or 3 or 4. So we can start further on. That's a subsequence. Okay, we've just thrown away a few terms. That's the original sequence, just without the first few terms. Another subsequence is to throw away all of the odd terms. So we only take the values of the sequence in every other value of the sequence. Or, you know, anything else.
Okay.
Is that clear? Okay. Yeah, so you're just getting rid of some of the terms of the sequence. The subsequence is just the original sequence without some of the terms. Okay. And so this is the theorem they prove there. If xn tends to L as n goes to infinity, okay, and nr is some strictly increasing sequence of integers, okay, so in n, n r in n, and nr strictly less than nr plus 1. These two things together imply that x of n sub r tends to L as r goes to infinity. Okay, so if you've got a sequence that's converging, if you take any subsequence of that converging sequence, then that also goes to the same limit. Okay, so if like the sequence 1 over n, that tends to 0 as n goes to infinity. If we only look at the even terms from that sequence, it's still going to go to 0.
Okay.
Makes sense. And the proof is very straightforward. As we know, xn tends to L as n goes to infinity. If we let epsilon bigger than 0, then there exists n in capital N and n, such that for all little n bigger or equal to n, absolute value of xn minus L is less than epsilon. Okay, but we know that n is strictly increasing. NR is strictly increasing, so so for any r, for all r in n, it must be the case that n sub r is greater or equal to r. Okay, if you think about strictly increasing sequences, you know, you could have 0, 1, 2, 5, 7, 9, 23, I don't know. Because in each step of the sequence you have to go up by 1, and every time you must be at least as big as the element of the sequence. Makes intuitive sense. Okay, so because for all r in n, nr is bigger or equal to r, we know that for all r bigger or equal to n, n sub r is bigger or equal to r, which is also bigger or equal to n.
So for every r which is bigger
Than this n we found previously, then we know that it's always the case that nr is bigger or equal to r, and we kind of assume that r is bigger or equal to n, so nr is bigger or equal to n. Okay, but if nr is bigger or equal to n, we know that it's the case that xnr minus L is less than epsilon. Okay, so we've proven then that xnr tends to L as r goes to infinity. So that's all we needed. Oh, can I represent? Yeah. Yeah, we've done that. It's a bit difficult. So this can be useful because sometimes, sometimes a sequence will look very messy, but if we take a subsequence of that sequence, we'll end up with something that's it's a lot easier to prove that it converges. Can we do any of these examples? That one's okay, so here's an example in this exercise. Maybe we'll have a go at this exercise. So So previously, in a previous exercise, which we didn't do, they showed that it was certainly the case that n to the 1 over n converges. Okay, I think they did that by bounding it. Okay, by showing it's bounded, any bounded sequence. So it's going to be increasing. Is it increasing? No, sorry, it's decreasing. It's decreasing and bounded, so it's going to converge. Is that right? Yeah. Yeah. So the sequence is 1 to the power of 1, which is 1, then 2 to the power of a half, which is square root 2, so 1.4 something. Let's have a look at that exercise. It was 420, part 6. Prove that the sequence n to the power of 1 over n decreases for n bigger or equal to 3. Okay, well let's take it as given, but you can prove that. So to start, the sequence is clearly increasing to start with. It goes from 1 to 1.4 something or other. But then 3 to the power of a third is... where is it? 3 cube root of 3 is also what is 1.44 something or other. It's very similar to what's the square root of 2, 1.2, that's 1.41. So the first three terms are increasing, but then 4 to the power of a quarter, I should be able to work that out. So the square root of 4 is 2.
Oh, yeah.
Yeah. So 4 to the power of a quarter is the square root of the square root of 4. So it's the square root of 2, which is 1.41 again. Okay, so, and from then on, the sequence is decreasing. Okay, so the sequence is eventually decreasing, so it's bounded, so it converges to something. Okay, so we know that the sequence n to the power of 1 over n converges to something, and that was proven previously. Okay, and the claim is that the sequence n to the power of 1 over n converges to 1 in particular as n goes to infinity. And it says you can do this by considering the subsequence 2n to the power of 1 over 2n. So if we can show that 2n to the power of 1 over 2n tends to 1 as n goes to infinity, then as we know that this is a subsequence of n to the power of 1 over n, right? This is all of the even terms from sequence n to the power of 1 over n. So if this tends to 1 as n goes to infinity, then this also must tend to 1 as n goes to infinity. Okay, so by considering a subsequence which is easier to work with, you can prove that a sequence converges. Yeah, I expect proving this you will use results that they've proven previously. I don't think it's worth going through in detail, but this is 5.7. Use this as a bookmark. It's not too difficult actually. What how they show this. Is they, so you can split this in 2 bits. So this is 2 to the power of 1 over 2n times n to the power of 1 over 2n. And this bit's kind of, so this is a product of things. So it's a product of that and that. If we can show that this converges to 1 and this converges to 1, then because we showed that products of sequences converge to the product of the limits, will be done. Okay, so first thing to show is that this converges to 1. Well, how do we show that that converges to 1? Well, we want that 2 to the power of 1 over 2n minus 1 is less than epsilon. Okay, so...
Sorry.
oh, thank you.
I heard you this for later. I forgot you first of all.
Oh, don't worry, thank you.
Sorry.
So we can rewrite this as 2 to the power of 1 over 2n is less than 1 plus epsilon, 1 minus epsilon. That's what we need. So this is if and only if. So if we take the logarithm of both sides, okay, so log, this is true if and only if log of 1 minus epsilon is less than 1 over 2n log 2 less than log 1 plus epsilon. You don't remember the rules of logarithm, it's probably a long time. So this is true. Then we can divide by log 2. So this is log 1 minus epsilon divided by log 2. And we can multiply by 2 as well at the same time. 2 is less than 1 over n is less than 2 log 1 plus epsilon over log 2. So this is, again, these are all if and only ifs. So then we can flip the signs. So this becomes 2 log 2 over log 1 minus epsilon is greater than n is greater than 2 log 2 over log 1 plus epsilon. So we need so we want to find a lower bound on n, right? We want n to be sufficiently large. Okay. So remember that the definition is that it has to be some point beyond which you're always close. So this looks like a lower bound. Problem is we also seem to have an upper bound. I haven't made a mistake somewhere, have I? So, oh, of course. So, remember what the logarithm function looks like? So, log of x looks like this. Okay, you see logarithms a lot in economics. It's useful to remember what these things look like. And it crosses at 1. So given this crosses at 1, what mistake have I made?
We cannot have log 2 or...
No, log 2 is not the problem. So it just goes negative below 1. So this is fine. You know, we can take if we take the logarithm as an increasing function, okay, so if a is less than b, then log of a is less than log of b.
Yeah.
That's fine. So that's true for any increasing function, you can do that. So here this line was fine. This line was fine as well, we've just divided by 2 and divided by log 2 multiplied by 2. So up to here we're fine, but this next step I made a mistake. Okay, and the problem was that this is negative. Log of 1 minus epsilon has to be less than 1, because epsilon is positive, so this thing is negative. Okay, so if this is negative, then we can't then, so if a is less than 0 is less than b, okay, it's not the case that 1 over a is greater than 1 over b, because a is negative. Okay, so this is a negative number. So I made a little mistake there, but we know this thing is negative. Okay, so it's not. So all this bound says is that 1 over n is bigger than something negative. So in fact we can just replace that bound with 1 over n is bigger than 0, because we know 1 over n is bigger than 0 anyway. Okay, so this is our bound. N is bigger than 2 log 2 over log 1 plus epsilon. Okay, so if we take capital N equal to that thing, that's 1 or something. Okay, we take capital N bigger than this thing, then for any n bigger than capital N, distance is going to be less than epsilon.
Okay. So I'm confused. What we are trying to prove?
So we were doing this too. So ultimately we were trying to prove that 2n to the power of 1 over 2n tends to 1.
Okay.
And to start with, we were just looking at this term, 2 to the power of 1 over 2n.
Okay, that we need to prove first that the first
the first term tends to 1.
Okay.
So what we've done, we had 2 to the power of 1 over 2n minus 1.
Yeah.
It's less than epsilon. This was true if and only if this, if and only if this, if and only if this. Okay, so we've discovered that if n was bigger than this thing, then it must be the case that this is less than epsilon.
Okay.
You know, if you like, you can work backwards. You can get to this point and then you can work backwards. So you said, well, let's take n as this, and let's suppose that little n is bigger than this, then little n is certainly bigger than this. Okay, so 1 over little n is less than this, so 1 over 2n log 2 is less than this, so this is less than that,
So yeah, you can go above.
Yeah.
Okay, so where did you find, you name n, the big N, the capital N.
As this thing.
The +1, where is that one coming from?
The +1 is because I normally do all n bigger or equal to n, and that was a strict. It doesn't, you know, as long as, you can always make capital N bigger, and it doesn't hurt anything.
Okay.
Remember, the definition says, beyond a certain point, you have to be sufficiently close. Okay, it doesn't matter where that point is. That point can be arbitrarily far along. So, you know, if beyond from, I don't know, from the 10,000th element onwards, you're sufficiently close to the limit, then from the millionth element onwards, you're also sufficiently close to the limit. So once you've found an n, you can always make n bigger without causing any problems.
Okay, just leave it for a while.
Okay.
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 Mhm.
Um, so we know that this converges to something,
Mhm.
2n to the power of 1 over 2n, because it's eventually increasing and bounded. And we know that this converges to 1. So whatever this converges to, whatever this thing converges to, this must also converge to that thing. Okay. You can show that this converges to something by the same argument as you show that this converges to something. Okay, so if 2n to the power of 1 over 2n tends to some limit L as n tends to infinity, then it must also be the case that n to the power of 1 over 2n tends to L as n tends to infinity.
Mhm.
Because this is tending to 1, the product of limits has to tend to the limit of products. Okay, so this thing will tend to 1 times the limit of this. Okay, so it must be L. So what we've proven is that n to the power of 1 over 2n tends to L as n goes to infinity, and 2n to the power of 1 over 2n tends to L. So this is like okay, so let's look at this sequence. And remember, we also proved that n to the power of 1 over n must also tend to the same limit.
Mhm.
Okay, remember? So okay, we're trying to prove that it tends to 1, but we know that it tends to some limit n. Okay, so if we started by showing that n to the power of 1 over n converges to some limit, remember, let's call that limit L. This is a subsequence, 2n to the power of 1 over 2n, so if this converges to L, this must also converge to L. Then we showed that 2 to the power of 1 over 2n tends to 1, so this thing, n to the power of 1 over 2n, must also converge to what? To L. Okay? So we know that n to the power of 1 over 2n tends to L, and that n to the power of 1 over n tends to L. But we also know that by the product rule, n to the power of 1 over 2n times n to the power of 1 over 2n, that must converge to L times L.
Mhm.
Because we know this converges to L, so the product must converge to L. But what's this thing? On the left hand side?
Is it? No, I'm confused a bit.
Okay, let's go back a bit.
Yeah, if you take it from the first, n 1 over n tends to L, then you said the second 2n tends to L as well, right?
Yeah, because this thing tends to L because it's a subsequence. We're just taking
Okay.
every other term in this sequence. So we're taking all of the even elements of the original sequence. So if the subsequence converges, it converges to the same.
Okay, but then why 1 over 2n doesn't tend to L as well? It's not a subsequence that? This, yeah, the
Because-
first term.
So the so the sequence is n to the power of 1 over n. So what we've got here is, so I don't know, you know, it's like you've got 1 to the power of 1 over 1,
Mm-hmm.
2 to the power of 1 over 2, 3 to the power of 1 over 3, 4 to the power of 1 over 4, 5 to the power of 1 over 5. Okay, this is our original sequence.
Mm-hmm.
This subsequence is 2 to the power of 1 over 2, 4 to the power of 1 over 4, 6 to the power of 1 over 6.
Yeah. Mm-hmm.
Okay, it's every other term. But this thing is 2 to the power of 1 over 2, 2 to the power of 1 over 4, 2 to the power of 1 over 6, 2 to the power of 1 over 8. These terms aren't in this sequence. Okay, so this isn't a subsequence of that.
No. Okay. Okay, I see.
Yeah?
Okay, so we don't bother about that. We can say, right? So okay,
So we
proved.
prove
Yeah.
that this tends to 1.
Okay.
So this bit tends to 1. We know that this converges, so by the product rule, this times this must tend to the same limit as this. So 1 times whatever this thing's limit is must
Yeah,
be equal
uh-huh.
to L. So this thing's limit must be equal to L.
Okay. Okay. So yeah.
So oh, that I'll just read it. Okay, so that line. Well, so this implies that n to the power of 1 over n, 2n must tend to L.
Mm-hmm.
So by the product rule, n to the power of 1 over 2n times n to the power of 1 over 2n must tend to L times L. But what's this thing here?
2n. No.
So this is n times n to
And
the
so
power of
should-
something times n to the power of something.
So it's not n plus n and all. I have forgotten the.
So if you have x to the power of a
Yeah.
times x to the power of b, that's x to the power of a plus b.
Okay.
So it's like, think of x squared times x cubed. So x squared is x times x cubed is x times x times x. So in total you have x times x times x times x times x.
Mm-hmm.
2 plus 3 is 5.
Okay.
So this is,
It should be n. So it is 2 over 2n. So it is 1 over n. Yeah.
yeah. Okay, tends to n squared, L squared, but, so we started by saying n to the power of 1 over n tends to L.
Mhm.
So a sequence can only have one limit, we proved that yesterday. So it must be the case that L equals L squared, therefore L equals 1.
Okay. Okay, so now we prove the second term, right? That tends to n.
Yeah, so we prove them that this is 1, this is 1, this is 1, this is 1, everything's 1. All these things are tending to
Okay.
1.
Okay, let me write it down.
So this is why subsequences can be useful, but sometimes it's easier to prove things if you can
Mhm.
work with the subsequence. Not easy, these exercises.
I have not seen it before, I think, subsequences.
No.
This is the first time, yeah.
Okay.
Yeah. Okay.
Okay. Is this working? Ah. Okay, so that's one useful thing. Subsequences, but sometimes you can prove convergence a bit more easily. The most important thing is this theorem, though. This is a very famous theorem, the Bolzano-Weierstrass theorem. And yeah, the theorem's up here. And the theorem is that every bounded sequence of real numbers has a convergent subsequence. Okay, so if we think about the sequence 1 minus 1, 1 minus 1, 1 minus 1, okay, clearly has a convergent subsequence, namely 1, 1, 1, 1. Okay. Okay, so, it's a slightly surprising result. Maybe it's not. So, you give me any sequence, as long as it's bounded, even if it doesn't converge, I can at least find a subsequence of that sequence which converges. Okay, so you can't, you might think that you could jump around and make sure that, all points are always a long way from all other points. Well, eventually there's going to be a convergent subsequence there. So before we prove that, we have to prove a kind of an initial result. And that's for every sequence has a monotone subsequence. So monotone means always increasing or always decreasing.
Yeah.
Okay, and if we know that if it's bounded, sequence is bounded and either increasing or decreasing, then it must converge. Okay, so once we prove them that it has an increasing or decreasing subsequence, it's very easy to prove that it's convergent. Okay. So if we've got some sequence of numbers, we want to construct the subsequence which converges. So n greater than. Okay, so what happens so the proof works by distinguishing two different cases. So what we do is we define some sets, let's call them S capital N is the set xn n greater than n. Okay, so for any capital N, we define this set, which is the values the sequence takes from times beyond capital N. Okay. And there are two cases. So the first case is, if we're really lucky, it might be the case that every single one of these sets has a minimum. Do I mean minimum? A maximum, sorry. So these sets all have infinitely many elements, right? Potentially, because we're looking at all numbers bigger than n, so they can be arbitrarily far into the future. So this might be a set with infinitely many elements, and a set with infinitely many elements might not have a maximum, okay? But if we're lucky, every element of the set has a maximum. Okay? So in that case, we're lucky, and every element, each of these SNs has a maximum, then we can define a new subsequence where xn1 is s of 1. Okay, so this is s of 1 is the or s of 0 even consistent. So s of 0 is the maximum of all numbers bigger or equal to 0. Okay, so it's the maximum over every element of the sequence, over the entire sequence. Okay, s of 0 is the maximum of the values of the sequence for numbers bigger or equal to 0. Okay, so it's the maximum of the whole sequence. So that's as high as it possibly can be. And then let's define xn of 2 as as the no, it doesn't. I do it a bit the way I want to do the strings. Okay, so x of so if we look at s of 0, that's for maximum of all elements apart from the first one, and it's going to be some element of the set. Okay, there's going to be some n which is equal to the maximum of that thing. So let's let me give you an example to make things clearer. So suppose we have 1, a half, a third, a quarter. Suppose that's our sequence. Okay, so we define S of 0 is the set of all elements bigger than 0. Okay, so this is the 0th element, this is the first, this is the second, third, fourth, etc., etc. So S of 0 is a half. It's for maximum. S of 0 is all of this set, sorry, beyond.
Why is that? We
So
need everything beyond 0, right?
Yeah, all of the elements beyond 0.
When 0 is the first element?
Yeah.
Okay.
Okay, let's call the first element 1, because it makes things clear. It really doesn't matter what you call the first element, I suppose. So let's work with the first element being 1 for now. So S of 1, okay, is the maximum of all of these elements where n is bigger than 1. Okay, so it's the maximum. S is the set. So S of 1 is this set. I'll be very clear. Sorry, half, third, a quarter, a fifth. Right? It's etc. etc. It's all of the elements apart from the first one. Okay, the maximum of that set. Well, that's just equal to a half. Okay, so that was a particular element of the sequence. Okay, so we can find a particular n sub 1 which tells us which element of the sequence that was. Okay, so here n sub 1 will be equal to 2. Okay, because the second element of the sequence is equal to the max of S1. So for x, we then define the next element is the max of S n sub 1. So now we're looking at all of the elements beyond half. So this is going to be equal to a third. And x n sub 3 is going to be equal to max s sub n2, etc., etc. So in this case, our subsequence is just going to be the original sequence without the first element. But if we had a slightly different sequence, you know, suppose we had suppose our sequence was something that isn't going to look like it's and we always want them to be a maximum. I don't want it to convert exactly. So what about this? Let's take 1 minus 1, a half minus 1, a third minus 1, a quarter minus 1. Okay, that's a sequence which clearly doesn't converge. because every other term is minus 1. But we can see it has a convergent subsequence, right? It has 1, a half, a third, a quarter as a convergent subsequence. So let's apply this construction to this sequence. So what we get, well, the first element, so S of 1 is the maximum of all of the, so S of 1 is the set of all of these values beyond there. The maximum of all of them is going to be a half.
Mm-hmm.
Okay, so if we number from 1 again for make things easier. This is picking up the third element. Okay, so we're taking n of 1 is equal to 3. Our construction then says that we take the maximum of S sub n1. So S sub n1, well, this is all of the elements of xn where n is bigger than n1. n1 was equal to 3. So we're taking the maximum of all of these things beyond 3.
Mm-hmm.
Okay, so the maximum is going to be a third, which happens to be the fifth element. So n2 will be equal to 5. When we do it for n3, n3 is going to be equal to 7, and so on. Okay, so this construction here is picking up the convergent subsequence.
Why is 3? It should be half or not? For example, n1 equals 3.
So n1 is the n1 is the value, is the element of x which is the maximum of S1. Have you seen this notation? Argmax, maybe doing it this way is clearer. So if you've got some set S, is the argmax of S.
I haven't seen that. No.
Okay, so the maximum of a set is the value. Well, I don't know. Let me explain it again. So n1
Mm-hmm.
is the index into our sequence. So
Mhm.
these are the indexes 1, 2, 3, 4, 5, 6, 7, 8, okay, etc. Where the x of that index is equal to the max of S1. Okay? S1 was all of the elements after the first one.
Okay.
So the max of S1 is a half.
Not 3. Why you have put down 3? That was my question. So the
Yeah.
maximum should be half.
Yeah, so the maximum of S1 is a half,
Yeah.
but that is the third element. So n1 is equal to 3. X of n sub 1 is a half.
Okay. So x3.
X of n sub 2 is a third. X of
Okay.
n sub 3.
Yeah. Okay.
You see the distinction? So this is n, this is giving you the index. Okay, so
Okay,
we're
mhm.
constructing a subsequence. We're choosing indices which are going to give us this.
Okay.
the subsequence.
I see.
Okay. Okay, so this construction, you can continue this construction forever.
Mm-hmm.
At each point you're finding an index, a new index, n1, n2, n3, and it will always be higher than the previous index, okay, because of this set. Sn is the elements xn where n is strictly bigger than n, okay, so you're only looking at indices strictly bigger than your old one. And if you like, this first one is the maximum over a large set, then when we look at the next one, we're then taking the maximum over a slightly smaller set, okay, because we've taken out some elements from the start. So if we've gone from a maximum over a big set to a maximum over a small set, the number must have gone down, okay, at least weakly.
Mm-hmm.
Okay, so it must be the case that xn1 is greater or equal to xn2, which is greater or equal to xn3, etc., etc. So xn sub r is a decreasing subsequence. Okay, so if it really was the case that every one of these sets S sub n had a maximum, then we could certainly construct a decreasing subsequence. Okay, so this is one possibility. But maybe we're not lucky, maybe one of these sets doesn't have a maximum. Okay, so for some n, S sub n doesn't have a maximum anymore. Okay, so then we're going to look at a second case, and in this second case we're going to have, rather than a decreasing subsequence, we're going to end up with an increasing subsequence. So there must be must exist some, what do they call it, n1. So in the second case, there must exist some n1 in n, such that the supremum of Sn is not in Sn. Okay, that's another way of saying that Sn doesn't have a maximum. Okay, if Sn has a maximum, then its supremum is equal to its maximum. Okay, but if it doesn't, then the supremum will be something outside the set. Okay, so think of 0, a half, 0, a half, 3/4, 5/8. Okay, that sequence. Or so the supremum of that set of all those infinitely many elements is 1, but that 1 isn't in the set. Okay. Sorry. So remember, E means an element. I'm not sure if I ever told you that. Not that means not an element. Okay, that's what I meant. So there must be some n1 such that the supremum isn't in the set. Okay, so for any, suppose we have some n bigger or equal to, this is n1, sorry. Suppose we have some n bigger or equal to n1. Well, they call it, maybe they call it n. Let's call it n. Then it can't be the case that, so if we remember what S sub n1 is, well, that's all of the elements beyond the point n1. Okay, so x, if m is bigger than n1, then x sub m is in S n1. Okay, just by the definition of what this set S is. Okay, it's all of the points beyond a certain time. Okay, so if we have some m beyond that time, then x of that m must be in the set. Okay. So x sub m can't be a maximum. This set doesn't have a maximum, so x sub m isn't a maximum. Which means there exists some other, there exists n bigger than m, okay, such that x of n is bigger than x of m. Because if it didn't exist an n bigger than m with xn bigger than xm, then xm would have been a maximum.
Okay.
So what do I do by xm1? So this is true for any m bigger than m1. We can always find a later term that's bigger than Okay, because otherwise, so if it was the case that at some point there was no later term that was bigger than it, then if you like, we'd have the set before that time and the set after that time. Set after that time has no element bigger than the one we've currently found. Set before has finitely many elements, so then we'd have a maximum.
Okay.
Well, so okay, so we have these two cases. Let me step back a bit. We had two cases. One was all of these sets have a maximum. The second case was there's eventually a set which doesn't have a maximum. Okay, so there's some set which doesn't have a maximum. It's just another way of saying doesn't have a maximum. So for a set not to have a maximum, then if a set doesn't have a maximum, if we split that set in two, at least one of those halves must not have a maximum. Okay. So one way we can split Sn1 in two, well, Sn1 is equal to all of the xn's where n is greater than n1 and n is less or equal to m. So it's a combination of this set and another set, xn, n greater than n strictly greater than m. So this means union. It means take all the elements from one set, take all the elements from the other set, stick them together. Okay, so Sn1 was all of the elements where the index was bigger than capital N1. We can split that in two. We can think of it as all of the elements where the index is bigger than capital N1 and the index is less or equal to m. So that's one set. We can think of it as that combined with the set of all the elements of xn where the index is bigger than m.
Yeah, but if we combine that, we will not get n greater than n and n equal to m, or because you say that we combine that and you have in one case n less or equal to m, and on the other case
m bigger than m.
yes. So what?
So in one half we have all of the elements where n is less or equal to m, and the other half we have all of the elements where n is bigger than m.
Yes. So if we combine that, we
yeah. So if we combine that, we just get these two bits kind of cancel out, and we're just left with all the elements bigger than n1. Okay, because n is bigger than n1.
Okay.
Okay. So we can kind of think about splitting Sn1 like this. Okay. And this set has finitely many elements. M is finite. So this is a set with finitely many elements, and this set certainly has a maximum. Any set with finitely many elements has a maximum. Okay, so if this has a maximum, let me write, has a max, but this doesn't have a max, then it must be the case that this doesn't have a max. Okay? So this is just this set here is just equal to S of M, isn't it? So all we're saying is that if the sum n1, where S sub n1 doesn't have a maximum, then any number bigger than that, S of that number also doesn't have a maximum. That's why I'm saying the same thing. So okay, so we've got these sets. Okay, so xm1 is xm1 plus. Okay, so the answers, the proof suggests that we take xn1 equal to x of capital N1 plus 1. Okay, remember capital N1 was this point beyond which the sets don't have a maximum. And we're taking the next element. Okay, then we take xn2 as first term following xn1 for which xn2 is bigger than. Okay, so remember, so it's the first term following n1. Okay, so the set S sub n1. So if you like here, we're setting n1 is this is equivalent to saying n1 is equal to capital N1 plus 1. Okay. So n1 is bigger than capital N1. So S of capital N1 doesn't have a maximum. So S of capital N1 must contain at least one element which is bigger than x of n1, because if it didn't, then yes, it's the same idea again. We can think about splitting. Think about splitting S sub n1 into xn n greater than n1 n less than n1. So we've defined n1 as n1 plus 1. We want to find a term xn2 which is bigger than xn1. Okay. If there was no term bigger than xn1, then xn1 would be a maximum of S sub n1. Okay, so eventually there must be an element bigger than xn1. Okay, so eventually there's another term xn. There's another term xn2 where xn2 is strictly greater than xn1. I think that's all there is, isn't it? Given only xn. So likewise, so now we can do the same thing again. So remember that, so S sub n1 doesn't have a maximum, S sub n2 doesn't have a maximum. Okay, so because we showed that each of these beyond capital N1 doesn't have a maximum. So because S sub n2 doesn't have a maximum, there must eventually be a term bigger than x sub n2. Okay, so we can find x n3, which is bigger than x n2. Okay, this thing continues forever. Okay. Sorry, I haven't been particularly clear. You get the idea?
Yeah.
Yeah, okay. So you can find an increasing subsequence. Okay, so the proof, so to kind of summarize the proof, we had these two cases. We made these sets Sn, and the first case was suppose that each of them has a maximum. Okay, then we found a decreasing subsequence. If eventually one of them doesn't have a maximum, then we showed that all future ones don't have a maximum, and that means that there must be an increasing subsequence. So in one case we have a decreasing subsequence, in the other case we have an increasing subsequence. Okay, so every sequence must have a monotone subsequence. Okay, thus every bounded sequence of real numbers must have a convergence subsequence. Okay, which follows straight away. So the lecture notes go on to define lim sup and lim inf, which you'll see a lot. You know, some of the things Antonio will teach you in macro, he'll be using lim sup and lim inf, so we might as well define them. Lim sup of some sequence, so xn, n, n. This is, you can think of it as the limit as n goes to infinity of the supremum of the set xn n, let's call it x sub k, k greater than n. So these are like the sets we were looking at before. So this is saying we take the supremum of all points beyond a certain point, and then we take the limit of that as the cutoff goes to infinity. Okay, so in this case of, I don't know, a sequence that looks like so here's the sequence. If we take oh, I've done this wrong way around, I'm an idiot. Suppose it looked like this, so so it's kind of oscillating between these values, suppose the sequence as well. The maximum from the start onwards, the supremum from the start onwards is this point. Okay, so our first, we need another colour. So our first supremum is this. Our second supremum is the maximum from this point onwards. Well, that's that. And then our third supremum is also that one. If this is 1, this is 2, this is 3, this is 4, this is 5, I'm not quite in line. Okay, then this is a supremum. So if we just look from there onwards, then this is the supremum. If we look from here onwards, this is the supremum. Okay, so this construction, the supremum from a point onwards, is defining a subsequence, and then we're taking the limit of that subsequence. Okay, so this is called the limit superior of the limit inferior. If something has a limit, if a sequence has a limit, then lim sup n goes to infinity of x n will be equal to lim inf n goes to infinity of x n. This is true if and only if lim xn exists. Okay, so if the sequence has a limit, then the limit sup and lim inf Whoa, but they're grey. And you can see that this is exactly the construction we used in the Bolzano-Weierstrass theorem.
What? Just okay. We found the supremum, right?
Yeah.
What is the infimum? Why do we say that this is-
lim inf is just defined the same way. So lim inf n goes to infinity. N goes to infinity. Xn, well, that's equal to lim n goes to infinity of the infimum of the set xn and xk, sorry, k greater than n. Okay, so it's slightly confusing. We write lim sup as if it's two words, but really it's not. Lim sup is just one thing. It's just kind of one operator on this sequence, but it's just defined as the limit of the supremum from a certain point onwards. Okay, so if a sequence is decreasing, then the lim sup will be decreasing. If a sequence was increasing, then, so suppose we had, okay, the supremum from here onwards is, I don't know, somewhere around here. The supremum from here onwards is also somewhere around here. Okay, so for an increasing sequence, the limit superior is just going to be a constant. Because the supremum I give up. The supremum from here onwards is, like the largest this is ever going to get to, which is here. But if you go a bit further forwards, if this is increasing, then the supremum is still the same thing. It doesn't matter if you get rid of a few small values at the start. The supremum's still always going to be the same thing. Okay, so for an increasing sequence, the lim sup is going to be a constant. But the lim inf will be, so the lim inf, if you like, is the minimum from here on in, okay, which is here.
Yeah.
Then the minimum from here on in, which is here. The minimum from here on in, which is here. Okay, so for an increasing sequence, the lim inf will be the original sequence, and the lim sup will be a constant.
So when it was decreasing, you had a constant infimum.
Yeah,
and
exactly.
Then it was again.
Yeah, okay. So you get the and it's normally easier to prove things about lim sups and lim infs. So, sometimes results are written in terms of lim sup or lim inf, because that's all you need. But the textbook kind of introduces lim sup and lim inf here, but then doesn't actually do very much with them.
Yeah.
Let's take a break, because you clearly. Yeah, so we can go till 2:45. So if you take like 5 minutes or something.
are you doing,
I'm
Kitty?
doing a bad job. It's still going. I should stop it.
I don't know when my meeting is.
Okay, you ready to carry on?
Yeah.
Okay, so we won't say anything more about lim stuff and limits. So the next important thing we've got to look at are what's called Cauchy sequences. So the moment, in order to prove that something converges, we've always had to know what the limit was. Okay, and we're always looking at expressions like xn minus L. But a lot of the time with funny sequences, we won't know what the sequence converges to. Okay, so without knowing what the limit is, it'll be very hard to prove what it converges to. If you knew what the limit was, then maybe you could prove what it converges to, but often you don't know what the limit is ahead of time. So you'd like to be able to prove that it converges to something at least. So rather than looking at xn minus the limit, we might be tempted to look at xn minus xm, where n and m are both bigger than some number. Okay? So rather than looking at the distance from the limit, we might want to look at the distance between terms in the sequence. Because if you think if the sequence is going to converge, you think that probably the terms are going to get close together as time goes on. And this is the idea behind Cauchy sequences. So what is a Cauchy sequence? Well, so we say that something is a Cauchy sequence if for all epsilon greater than naught, there exists capital N in the natural numbers, such that for all m greater than n and n greater than n, or greater or equal to, whatever you like, xm minus xn is less than epsilon. Okay, so any sequence satisfying that we call a Cauchy sequence. So what's this saying? It's saying beyond a certain point, it doesn't matter if you take like a point in 1,000 periods or a point in 10 periods, the distance between any 2 points beyond that point will be sufficiently close. Okay, so we might hope that if a sequence satisfied this property, then it will also converge. And indeed, that turns out to be a theorem. Every Cauchy sequence converges. Excuse me. So there are some little first results to prove. So the first one is that any convergent sequence is a Cauchy sequence. Well, this is fairly easy. If we know that it converges, then eventually the sum n such that xn minus L is less than epsilon. So if we take, so the sum n in n such that for all n bigger than n, xn minus L is less than epsilon. So let's take two different, so suppose m is bigger than n, bigger than capital N, and n is bigger than capital N. Then it's true for both that xn minus L is less than epsilon and that xm minus L is less than than epsilon. Okay, so x, what do we want? Xm minus xn. Well, that's equal to xm minus L plus L minus xn. Using that trick of introducing something, then reintroducing it by the triangle inequality that's less than xm minus L plus L minus xn. Okay, which is less than 2 epsilon. Okay, which will do. Okay, so any convergent sequence is Cauchy. What's the other one? Any Cauchy sequence is bounded. How might we prove that? Any Cauchy sequence, or any sequence satisfying this, is also bounded.
Then it should be xn less or equal than b, for example. Then we proved that, right?
So we proved that a convergent sequence was bounded.
Yeah.
So this claim is that any Cauchy sequence is bounded. How would we prove that? Can I start this?
So, I don't know, the absolute you have xm minus xn should be less or equal than b, and we take it from there, or?
Yeah, so if you remember what we did to prove a convergent sequence was bounded, we just took a fixed epsilon, so we took epsilon equal 1, I think. So we can do the same thing here. So we know that there exists n in n such that for all m greater than n and n greater than n, xm minus xn is less than 1. Okay, so we know that the set xn or xk, say xk k is less or equal to capital N. We know that set is bounded because it has finitely many elements. So all we have to do is show that it's also bounded from capital N onwards. So this is true for all m and all n. Well, let's just fix an n. Okay, so let's take little n equal to big N, or equal to big N plus 1, whenever you want. So we can have xm minus x big N plus 1 less than 1 for all m. So this is saying that xm is less than xn plus 1 is bigger than xn plus 1 minus 1. Okay, this is just a number, this is just a number. So x, so it's bounded from then on.
Okay.
So it's basically the same as the proof of
Yeah, but when you
convergence.
say xn plus 1 is a number,
well, so we know that for any m, it's not a function of m. That's what I mean.
okay.
So for any m, this is true. Okay, so for any m, we've got it that it's between these two lines. Okay, so it must be, so it's bounded. Okay, so those two propositions we've done, and now here's the big theorem. This is why they're useful. That every Cauchy sequence converges. And this is, we're going to use the Bolzano-Weierstrass theorem here. Okay, that was one about convergent subsequences. So, because it's a Cauchy sequence, it's bounded. Because it's bounded, it has a convergent subsequence by the Bolzano-Weierstrass theorem. Okay, so let's call the convergent subsequence XNR. XNR converges, so it converges to some limits. Let's call the limit of XNR L. So we have that xn sub r goes to L as n goes to infinity. So you can you know, it's kind of intuitive from this point already. We know that it has a convergent subsequence, which is tending to some limit, and we know that the terms are always fairly close to each other. Okay, so if it has a subsequence which is converging, and all of the other two terms aren't too far away from that subsequence, then you'd hope that the whole sequence is going to converge. Okay, so what does this mean? This means that for all epsilon greater than naught, there exists n in n. This is r. This is r in n, such that for all r greater than r, x n r minus l epsilon. Okay, that's just the definition of that. Oh, sorry, this is as r goes to infinity. Yeah. So let's we'll do our normal thing. We let epsilon bigger than 0. Then we know we can find n and r. Okay, so such that there exists n and r in n, such that all these things are satisfied simultaneously. This and this are satisfied simultaneously. Okay, so for all m bigger than n and n bigger than n and r bigger than r, xm minus xn is less than epsilon, and xn r minus l is less than epsilon. Okay. So let's take this is true for all m bigger than n. So if we take n star as the maximum of n sub r and n. So this is true for so remember n sub something is giving us the indices. This thing is true for kind of sub indices bigger than r. So let's look at n sub r plus 1. Okay. Then for all m bigger than n star and n, so if what do I mean? Let's get so for all n bigger than n star, n is bigger than n star. Okay, then n star is at least bigger or equal to this thing, n sub r plus 1. Okay. So right, so n is bigger than what we want is that we need, so what we need is that nr is bigger than n, bigger than capital N. So that's rubbing around. So if we take some r bigger than r, okay, then n sub r is bigger than n sub, okay, and n sub r is bigger than n sub capital R. Okay, because n is an increasing sequence. Okay, so n sub r is doesn't work, does it? I'm not trying to find things right. Sorry, let me just find the answer. This is right. Choose R so large for nr is bigger than n and r is bigger than r. Yeah, that's what we need. nr is bigger than n, r is bigger. Okay. Sorry. So we can choose. So, you know, n sub r is an increasing sequence. Eventually, n sub r will be bigger than n. Okay, for sufficiently large r, n sub r will be bigger than n. So, if you like, we can say there exists r2 such that for all r bigger than r2, n sub r is bigger than r. Okay, so for we define r star is max r comma r2. Okay, then if r is bigger than r star, then we know that r is bigger or equal, r is strictly bigger than r, and r is bigger than r2. Okay, this is what we need, sorry. So for r bigger than r star, r is bigger than r and r is bigger than r2. Okay, but if that means that nr is bigger than nr2, okay, and we know by assumption we defined R2 such that n, for all r bigger than R2, nr was bigger than R2. nr, oh, what am I doing? Sorry. So let me step back a bit. What we're trying to do is we want to be able to use this thing and this thing simultaneously. Okay, so we need r to be sufficiently big that r is both bigger than r, bigger than capital R, and nr is bigger than capital N. Okay, so this is what we need. So because nr is increasing, there must eventually be an r2 such that for any r bigger than r2, nr is bigger than n. Okay, so if we define r star as the maximum as the r we started with, and this r2, then if r is bigger than r star, then r is certainly bigger than r, and also r is bigger than r2, but we said that this is the definition of r2, for any r bigger than r2, nr is bigger than n. Okay, so we have that r is bigger than r, and we have that nr is bigger than n. Sorry, that's taking me a long time to get there. So this is what we need. So if we know this is true and this is true, then we can use this, okay? So let's take m equals to nr in this definition. So all we needed was for m was bigger than capital N. Well, we know that nr is bigger than capital N, so that's okay. So we know that for all n bigger than capital N, x nr minus xn is less than epsilon. And because we know xnr minus L is less than epsilon, we also have that xnr minus L is less than epsilon. Okay, so what we're really interested in is xn minus L, but this is the usual trick. Xn minus L is xn minus xnr plus xn minus xnr plus xnr minus minus L. Okay, so we've subtracted xnr, we've added xnr back. Xn minus xnr is less than epsilon. Xnr minus L is less than epsilon, so by the triangle inequality this is less than 2 epsilon.
Okay.
Okay, so xn minus L is less than 2 epsilon, so it converges.
Mm-hmm.
Sorry that took so long. Is that clear? Shall I go through it again? Or?
Maybe a bit, because you say that there exists R2 such that for every R small
Bigger.
Yeah, and then we have NR, or we need to prove that NR is larger than N capital.
So this is a statement. So the sum R2 such that for any R bigger than R2, N sub R is bigger than N. But this is just a consequence of the fact that NR is increasing. So I should have said, if you like, because N sub R is increasing. So it's an increasing sequence, strictly increasing sequence. At each step it's going up by at least 1.
So why?
Eventually it must be bigger than N. You know, any
Yeah.
increasing sequence must eventually be bigger than N. So there's some point beyond which it's always bigger than N. Okay, so R2 is just this point beyond which it's always bigger than N, bigger than capital N.
So why you write it again down NR larger than N? Is that a statement or?
Okay, so suppose we have some R bigger than R star,
Mhm.
then because R star is the maximum of R and R2,
Mhm.
then we know that R is bigger than capital R, and we know that R is bigger than R2,
Mhm.
just by definition of a maximum. Because R is bigger than R2, then NR is bigger than N.
Okay.
So if you like, this is just a fact,
Mhm.
okay, and then here we're using that fact.
Okay. Okay. Mhm.
It's confusing because you use the same letter all over again.
Okay.
But this is a general statement about all R bigger than R2. Here we've chosen some particular R bigger than R2. Okay.
Okay.
And then what we're doing is we're setting N equal to NR in this definition of the Cauchy sequence.
Mhm. Okay.
Okay, so it's quite intuitive. The Cauchy sequence condition says terms aren't that far apart once you go into the future. So if you know there's some convergent subsequence, then you kind of expect it to converge. And this is, this seems intuitive for real line. There are funny spaces you can work in which that's not true, but for real numbers this is true, which is a nice property. So if you want to prove a sequence converges, an easy way to do it is often to show that it's a Cauchy sequence. So that's why it's useful.
Okay.
You don't necessarily always, you won't be proving that every Cauchy sequence converges, but it's one of these facts that you can use all the time. Okay. So they've got an example here. Suppose you want to prove that this complicated sequence was defined recursively converges. Well, it's not very nice, but all you have to do is prove that it's Cauchy.
And you just take the theorem then that.
Yeah, and then you do. Okay, let's move on. What are we doing for time? 20 minutes. Okay, so next chapter is about series. What is a series? Well, a series is the sum of a sequence. My wife is laughing at me. So, if you've got some sequence an, okay, then a series is the sum from n is 1 to infinity or n is 0 to infinity, depending on how you're working. Okay, so a series is the infinite sum of the sequence. And when you're working with series, it's normally helpful to how do we do it? It's normally helpful to look at the partial sums. So S sub capital N, which is the sum from n equals 1 to capital N of an. Okay, so these are partial sums. So S sub capital 1 is just a1, S sub capital 2 is a1 plus a2, etc., etc. And we say that the series converges if the partial sums converge. Okay, so the meaning of this expression, n is 1 to infinity an, what that expression means is, well, that's the limit as n goes to, as capital N goes to infinity of these partial sums. Okay, so this infinite sum is just a shorthand for a limit of the partial sums. Yeah, and so this expression only has any meaning at all when this limit converges. Okay, if the limit doesn't converge, then the sum doesn't exist. Unless you're a physicist. So physicists like to work with non-convergent sums, but physicists don't use mathematics. So a non-convergent series we call divergent. So series diverges. So this example here is one that gets used a lot in economics. So suppose you're in fact, let's just suppose you have you buy a perpetuity. Perpetuity is an asset that pays you something for every period into the future. You want to value what that perpetuity is worth. Well, you're going to be discounting the future at some rate. So you care less about things in the future than you do now. And your value is going to look a bit like this. X is kind of your discount factor. Suppose the perpetuity pays you 1 unit in each future period, then your value is going to look something like that. So expressions like this occur all the time in economics. What does this thing mean? How do we show its properties? Well, we know that the partial sums, so the partial sums S sub n, which are defined by n, is 0 to capital N, x to the n. Well, they're just equal to 1, well, so this is 1 plus x plus, just 1 plus x to the n. So you've probably seen this 1,000 times. If you do 1 minus x times s sub n, okay, then you get 1 plus x. So from doing the 1 times Sn, you get the same thing. And then you get minus x times Sn, so you get minus x squared, minus x cubed, etc. up to the last term, which is going to be minus x to the n plus 1.
So you take out...
And then these all cancel out, exactly. So this is just equal to 1, which doesn't cancel, x minus x to the n plus 1, which doesn't cancel. So it's a 1 minus x to the n plus 1. Okay, so if 1 minus x times Sn is equal to 1 minus x times n plus 1, then Sn is equal to 1 minus x to the n plus 1 divided by 1 minus x. So these are our partial sums. The meaning of this thing is the limit of the partial sums. Okay, so this thing converges if this converges. Well, when is this going to converge? If x is bigger than 1, then this is going to explode, like 2 to the power of something explodes. So this sum is only going to be well defined if the absolute value of x is less than 1. Okay, in which case the sum n is not to infinity x to the n is going to be equal to the limit as n, as capital N goes to infinity, of 1 minus x to the capital N plus 1 divided by 1 minus x. Well, if absolute value of x is less than 1, this is going to go to 0, right? If you think half, half squared, half cubed, half to the 4. So this thing's going to 0, so it's just 1 over 1 minus x. Okay, so this is, so the value of a perpetuity is like 1 over 1 minus your discount factor. So that's something with a bit of economic application.
Yeah.
Yeah. Okay, then you can do other things. So it's useful to know whether a series is going to converge or diverge. So you might think that if the ANs converge to 0, that would be enough. What are these things proving? Okay, well, we'll get to that. Well, there'll be various conditions on AN which will mean the sequence converges. But it looks like the chapter is just giving you a few examples of ones that do and don't converge. So this sequence, sum n is 1 to infinity 1 over n, that diverges. I don't know if you knew that already. So this is 1 plus a half plus a third plus a quarter. This goes to infinity. So this doesn't converge. And how do we prove that? So one way to see it intuitively is that the sum, if you think about so think about the graph of 1 over n, it looks like that, okay? And a sum is a bit like taking it's a bit like an approximation to the integral, okay? What's the integral of 1 over x?
1 over?
1 over x.
What's
The integral of 1 over x. It's a long time since you saw an integral. So this, what's integral of 1 over x from, I don't know, 1 to infinity?
Ah, okay.
The integral.
Wow. It is. Well, if it was a number, it would be x1 minus, or I don't remember it very well.
So remember that if we differentiate, so dx to the n dx is nx to the n minus 1. So the integral is the opposite of the derivative. So we want n minus 1, that's not right, sorry, I'm stupid. The derivative of log x, do you remember what the derivative of log x is? Okay, it's useful, it would probably be useful to remind yourself of some derivatives. So the derivative of log x with respect to x is 1 over x.
Okay.
So 1 over x is the integral. So I mean log x is the integral of 1 over x. If when you differentiate log x you get 1 over x, when you integrate 1 over x you must get log x. Okay, so this is if you like it's log infinity minus log of 1, but log infinity is infinity.
And
I-
yeah, that's 0, yeah. So
Okay.
it's infinite.
So the integral is infinite, so that kind of suggests the sum is probably infinite as well. So this is kind of an intuitive argument, but can we prove it a bit more formally? Well, so all we have to do is to show that this diverges. Okay, so let's define Sn is the sum is this thing. We want to show that Sn goes to infinity as capital N goes to infinity. Okay, so we remember the definition of going to infinity. We need to show that for all capital K greater than 0, there exists n in N such that for all n bigger than N, Sn is bigger than K. Okay, well, this proof is quite clever. Let's just look at it up there rather than me writing it. So, let's look at s of 2 to the power of n. Okay, well so s of 2 to the power of n is 1 plus a half plus a third, okay, all the way up to 1 over 2 to the power of n. And then let's rearrange the terms in that sum. Okay, so we can think of, or just put brackets around them, I mean. So that's 1 plus, let's put the first 2 terms together in a bracket. And then the next 4 terms, a quarter, a fifth, a sixth, a seventh, okay, etc., etc.
Why do we do that? Do we put them in groups?
Because of the next step. yeah, you'll see. So remember we want to show that Sn is bigger than something. We want to show that Sn has to be, it can be made arbitrarily big. Well, if we want to we want to show that Sn is bigger than something, so we want to make everything smaller. So let's make a third, I'm not put the bracket in the right place. So 1 plus a half, 7 plus 1 over 8. So, sorry, I want to brackets around these 2 and then these 4. Okay. So this is, so we take it up to something that's 1 over 2 to the power of n. So the last term in each of these brackets is something that's 2 to the power of n. So 4, 8, the next one would be 16. Okay, so the last thing will be in brackets. Okay, so this is bigger or equal to 1 plus a half, let's keep that as it was. We want to make it, we want to find something smaller, okay, so let's make a third smaller, let's make it a quarter. Okay, so this is plus a quarter, plus a quarter. Here, in this one, we've got plus a fifth, sixth, seventh, eighth. Let's make these smaller, let's set them to an eighth. Okay, so this is 1/8 plus 1/8. 1/8. Okay, we can carry on doing the same thing. And what are these terms in brackets? Well, the first one is 1, then we've got a half. Quarter plus a quarter is a half. 1/8 plus 1/8 plus 1/8 plus 1/8 is 4/8, so that's also a half. The next term would be 8/16, which is a half.
Again,
Yeah. Okay, so this is lots of copies of a half. And how many copies are we going to have? Well, we're going to have capital N copies of a half. Okay, think about it. Capital N was 1. This would be, the last term would be a half. So we'd have 1. If capital N was 2, then we'd have a half, and a quarter would be the last term. Okay, so this is 1 plus capital N over 2.
Yeah.
So what are we showing? Well, we're showing that S2n is bigger than something that's increasing in n. Okay, so for any, so this is clearly enough, right? For any, if we want this to be bigger than k, all we need is that n over 2 is bigger than k minus 1, so n is bigger than 2 times k minus 1. Okay, so for sufficiently large n, Sn is going to be bigger than k. Okay, so it's going to infinity.
Okay.
Okay. And this theorem we won't go through. So this is a related one. If you've got the sum of, I'll write it here, 1 over n to the power of alpha, this is going to converge providing alpha is bigger than 1. Okay, if alpha is equal to 1, we showed it didn't converge. But if alpha is just a tiny bit bigger than 1, then it will converge. Okay, so in particular, like the sum of 1 over n squared, that will converge.
Okay.
And yeah, this certainly gets used. It's a useful fact to know, and it's only one that appears in economics, but we'll skip the proof of that. I'm afraid I'm going to have to stop. Let's do this at least, and then. So this is saying that if you take a linear combination of series, then it converges to the linear combination of the limits. This is really a straightforward consequence of what we showed before for sequences.
Yeah, I remember.
Okay. And this is an important property. If an converges, so this sum exists. So if that sum series converges, if it exists, then an must tend to naught as n goes to infinity. Okay, intuitively, if an didn't tend to naught, then late in the series would still be large terms. Okay, so your series would end up going to infinity. And the proof is very easy. So if we take the partial sums Sn, then let's, so here are Sn. Suppose S is this thing, for value of the series, then S capital N goes to S, as capital N goes to infinity. That's just the definition of the series. And it's also the case for S capital N minus 1, let's go to S as N goes to infinity. Okay, if we just shift the series forward and backwards, it can't change what it tends to in the limit. But then, what we're interested in is An. Well, An is Sn minus Sn minus 1.
Yes.
You see that?
Yeah.
So, because Sn is the sum a1 plus a2 all the way up to a capital N. Sn minus 1 is a1 plus a2 all the way up to a capital N minus 1. All these terms cancel out apart from a capital N. Okay? So, because this tends to S and this tends to S, An must tend to S minus S, which is equal to 1.
Okay.
So for any series, the terms in the series must tend to 0. So you might think that if the terms in a series tend to 0, so the underlying sequence tends to 0, then the series would exist, would sum to infinity. But it doesn't. And that 1 over n is a counterexample, right? 1 over n tends to 0, but the sum of 1 over n doesn't tend to something fine, it doesn't exist. And we better stop there. Let me give you some exercises. Have we seen any exercises here? So there are some here. So have a go at 521.1. That doesn't seem too bad. That looks a bit horrible. That looks a bit horrible. have a go at 521.4 as well. That's an important one. So so if you can have a go at 5 and 6 as well, because those are good. For any others, these are about lim sup and lim n. No, I don't do those. I did one of these subsequences. Maybe have a go at 3 from 5.7. It would give you another a practice of induction. Although it looks a bit difficult, but yeah, that'll do.
Okay.
Well, I suppose for lectures, but
So when a department is looking for a new head of the department, who is doing the interviews actually? Is it the people?
the dean mostly.
Ah, okay.
For a few people on the committee.
Okay.
But everyone's involved because it's going to affect everyone. I need my laptop. Yeah. Okay.
So
What did you try?
could we start with this exercise, which it seemed to be easy, but actually I couldn't get there. We have to,
Okay, so this is page 52.
yeah.
And how far did you get?
No, I didn't. I didn't
Okay.
know how to start it and where I should take it. Actually, we need to prove that
What page was it again?
52.
Is my book number different, 90? What exercise is it?
5.21, exercise 1.
Oh yeah, it's page 51 in mine. It's a different edition.
Ah, okay.
So what we're told that xn plus 1 minus xn is less than alpha to the n.
So we need to prove that Hn converge. Well, it is
Prove that xn is a Cauchy
a
sequence
Cauchy
and hence
sequence in
convergence.
terms, yeah. So how do we prove? Okay, the theorem is that absolute Hn minus Hm should be smaller than epsilon, right?
xm, yeah, exactly.
But how do we start it?
So it's much like a proof of convergence. So you're going to start by let epsilon greater than 0.
Yes.
So then we want to find an n such that for sufficiently large n, for m and n bigger than that capital N, what will be true? Well, we want xm minus xn to be less than epsilon.
Mm-hmm.
So that's what we want.
Yes.
So sometimes the way to do this is to work backwards. So this is, we know that this is true if and only if, did it say prove by induction? Did it give you a clue? So maybe this is something we could prove by induction. So, the condition we have here is a bit like a Cauchy condition. So this is saying the difference between successive elements isn't very big. Okay, so if this is true, what do we know about xn plus 2 minus xn? How would you get a bound on that?
I'm lost. What? So.
So just forget about that for
Yeah.
now. Just look at, suppose we wanted an upper bound on this, xn plus 2 minus xn. Can we use this to get an upper bound on this?
Can we?
Well, so we can do xn plus 2 minus xn plus 1 plus xn plus 1 minus xn.
Yes.
Okay, and then
This will be smaller or equal, yeah. And we take that, yeah, okay.
so let's see if this helps. So, you never know if something's gonna work, but you kind of have to guess what route you're going down. So this is this is exactly that. This is supposed to hold for all n, isn't it? So for all n in n, this is true. So it also holds here. So this is less than. So this is this, but push forward one period. So this is less than alpha to the n plus 1. This is less than alpha to the n. So it looks like we can kind of we could carry on doing this. So let's look at actually, but before we continue, look, alpha to the n plus 1, that's got to be less than alpha to the n. Okay, so this is less than 2 alpha to the n. Good enough. Well, let's leave it as a sum then. Okay, so we can kind of guess what's going to be true for we can kind of guess for xn plus k minus xn is going to be less than the sum from, I don't know, j equals 0 to k alpha n, sorry, j is 0 to k minus 1, alpha n plus j. Yeah, so this might be a reasonable guess. Remember we had the xn plus 2 minus xn was less than alpha to the n plus alpha to the n plus 1. And we've got xn plus 1 minus xn is less than alpha to the n. Xn plus 2 minus xn is less than the sum alpha to the n plus 1.
Yeah.
Okay, you can probably guess for xn plus 3 minus xn is probably less than alpha to the n plus alpha to the n plus 1 plus alpha to the n plus 2. That's just a guess, we haven't proven that. So this would be the general case. Okay, we've got the sum from 0 up to k minus 1 of n plus j. So maybe let's see if we can prove this as a first step. Okay, I'm not sure if this is going to work, but you just have to try things. Okay, so this is our claim. This is what we want to prove. So we're going to prove it by induction because it's got this k in. It seems natural to prove it by induction on k. So the case of k equals 0. Well, let's start with k is 1. So case k is 1, Well, this says that xn plus 1 minus xn, this is what we want to prove,
Yeah.
is less than, so this is a sum from 0 up to 1 minus 1, okay, which is 0, it's a
Yeah,
sum from 0 up to 0, so it's alpha to the n, okay. So this is what we need to prove, want to prove,
Yeah. Mhm.
but we're told this.
Okay.
Okay, so this just follows automatically.
Yeah.
Okay, we're told that, therefore there's nothing to prove. So suppose now, let's look at the inductive step. Inductive step. So suppose that for some k, xn plus k minus xn. So this is, the claim is for all k, this is true. Now we're just supposing that for some k, it's true. Some okay, and to use, what are we trying to prove here in the inductive step? What do we want to prove?
That xn is a Cauchy sequence. This is what we want.
Yeah, yeah. So that's where we're going. That's where we're going in the long run. But when we're proving something by induction, we do the base case. And the inductive step. What do we want to prove there?
Okay, so if it is true for 1 and we assume that it's true for n, then we need to prove that it is true for n plus 1.
Yeah,
right?
yeah. So here we're assuming it's true for k. We want to prove that it's true for k plus 1. Yeah, exactly. Okay, so what is xn plus k? Xn plus k plus 1 minus xn. Well, that's just as we saw before. That's xn plus k plus 1 minus xn plus k plus xn plus k minus xn. Okay, triangle inequality. So this is less than xn plus k plus 1 minus xn plus k plus. Okay, good. So this bit here, this is of this form, right? It's
Yes.
something plus 1 minus something. So this is less than alpha to the power of n plus k.
Yeah.
And this term, we've already assumed this term is less than that. So this is less than some j is 0 to k minus 1 alpha to the n plus j. Okay, the last term here is alpha to the n plus k minus 1. We now have an extra term on the end, which is alpha to the n plus k. So this is the sum from j is 0 to k alpha to the God, I hope this works. Alpha to the n plus j. Okay, so what we've proven now this claim up here. Okay, so can I wrap all this up?
No.
Well, okay. Let me just write somewhere else because I don't know if this is gonna.
Oh, okay.
I don't know if this is gonna work yet. What's this sum here? So what's the value of this sum? Can you remember?
For
So remember this trick I showed you earlier? Okay, so this sum, if we do 1 minus alpha times that sum, times sum j is 0 to k minus 1 alpha to the n plus j. Well, what's that equal to? Well, we get the original sum. Okay, so we get sum. This is what I showed you earlier. The n plus j. So we have the 1 term, and then we have minus alpha times this. So minus sum j is, if you like, j is 1 to k alpha to the n plus j. Do you see what I... So before we did it by writing out the sum, here I'm just doing it working with the with the sigmas. So So here we've got this term is just 1 times that term.
Yes, and what
And then
is
we
the
have
other?
minus alpha times this term. So what I've done, rather than, I could have done alpha to the n plus j plus 1.
Okay, so yeah.
But instead, I've just changed the indices. Before it went from 0 to k
Ah,
minus
okay,
1, so we were going from alpha to
mhm.
the n plus j, alpha to the n plus 0 to alpha to the n plus k minus
Okay,
1.
now it
Now
is
we go
here.
from
Mhm,
1 up to
mhm.
k. Okay? You
Yeah.
see what I've done?
Mhm.
So these are two sums, and all of the terms except the first and the last term are going to cancel out.
Ah, yes. I
Yeah, so it's
remember.
just
Yeah.
like what we had before. Okay, so this is so we get the first term from this one's left over, and then we get the last term from this
Yeah.
one. Okay, so the first term from this one is alpha to the n, and the last term from this one is alpha to the n plus k. Okay, so this sum over there is alpha to the n minus alpha to the n plus k divided by 1 minus alpha.
Mhm.
Okay. So what we're trying to get to is something of the form x to the m minus xn is less than epsilon. That's where we're trying to go. Where m can be m. Yeah. So the sum n such that if n and m are bigger than n, then this is true.
Mhm.
Okay, so if we look at what we have here, we've got xn plus k minus xn. So what we need is for this to be true for all k. So for large enough n, so here we have n bigger than n. So either n is bigger than m or m is bigger than n. So in either case, you can always write it as you can define one of them as like the smaller one. Let's call the smaller one n without any loss of generality, and let's call the bigger one m.
Mhm.
So we can have k is m minus n.
Yeah.
Yeah,
I understand that.
yeah.
Yeah.
So if we can, so maybe we can do something with what we have here. Okay, so this holds for all k. Xn plus k minus xn is less than that. We need to kind of get rid of the dependence on k. So we kind of need it. Okay, so what we have effectively is that xm minus xn is less than what is it? So alpha to the min m n minus alpha to the max m n divided by 1 minus alpha. You see what? So here we had n and n plus k.
Mhm.
So n plus k is like the maximum, n is like the minimum. So can we do a bit better? So as line is going through the middle. So we want something that doesn't depend on the maximum. Okay, if it only depends on the minimum, then it can depend on the minimum, because that's okay. If we say that the minimum of m and n is bigger than n, we can make sure the minimum is sufficiently large. Okay, but we can't do anything about the maximum.
Mm.
can I say it a different way? So we need a condition of a form nm bigger
Yeah.
than n.
Mhm.
Okay, so this is the same as a condition min n m bigger than n.
Mhm.
Okay, so we want this limit, this upper bound, we want it only to be a function of the minimum, not the maximum.
Okay.
Okay, that's all I'm saying. So all we have to do is produce an upper bound for this, which doesn't depend on the maximum.
Okay.
Okay, but this, well, it's kind of easy, isn't it? So, what upper bound could we take?
We can just take out max and we say that it's small.
So we can just take out this
Yeah,
term completely.
okay.
Okay, so we've got to make the whole thing bigger. So we might want to make the top bigger. We've got something positive minus something positive. Let's just get rid of the minus sign. So this is certainly less than alpha to the power of min m n divided by 1 minus alpha. Okay, so we
Yeah,
know...
but in this way we don't make it. For example, if you have alpha based on minimum minus alpha based on maximum, you get something smaller rather than having alpha minimum. No?
Well, we've got, so this minimum and maximum is a distraction. What we kind of have is we have xn minus xm, if you like, is less than a minus b divided by 1 minus alpha.
Okay, which
is less than a over 1 minus
okay.
alpha. So that's all we're doing.
Okay.
Does that make sense? So you can always make it something bigger by taking out a minus sign. So we have xm minus xm is less than this.
Yeah.
So we want it to be less than epsilon. So let's just suppose that this thing is less than epsilon. Well, when is that true? Well, that's true if and only if alpha to the power of min m n is less than 1 minus alpha times epsilon. So let's take logs. Okay, so remember that log of a to the power of b is b times log a.
Yes.
Okay. So this is min m n log alpha is less than and remember log a times b is log a plus log b. Log 1 minus alpha plus log epsilon.
Okay.
So we want min, what says m? What's supposed to be an m? Min m. Okay, alpha is less than 1, it said in the question, I think. Suppose that naught is less than alpha less than 1, it said in the question. So alpha is less than 1, so log alpha is negative. Okay, when you divide by a negative number, you have to flip the signs. Okay, so min mn is greater than everything else. Log 1 minus alpha plus log epsilon divided by log alpha. Okay. These are also going to be negative, so we've got negative divided by negative, so this thing will be positive. So all we need is that the minimum of m and n is bigger than this. Okay, so our natural candidate for the n is just this thing, So it was a nice application of induction. Maybe if there was a more direct way of doing it. Did you look in the answers?
Oh yeah, but I didn't understand. I don't know. I was not inspired at all. 21.
I don't know. I find this stuff quite fun. It's like I miss this stuff.
21. It was the first one, right?
So they got to the same bound, but we got to, well, so they took n greater than m, okay, whereas we kind of, we didn't make an assumption, but so they had alpha to the power of a minimum, which, you know, alpha to the power of a small one, so they're the same thing. So they did the same thing, but they just did it, they didn't prove it they didn't go through the proof. Yeah, okay, so we did it a bit more formally than they did it, but we did exactly the same thing. Okay.
Okay.
Good.
Well, just give me 2 minutes to write it.
I know this stuff looks scary, but it's all just practice, and you get familiar with this stuff, and then it seems slightly less scary. You know, but the way the PhD course is supposed to work is when you see the stuff, you're kind of scared by the stuff when you first see it. It all seems overwhelming. Well, you know, that's inevitable. There's not much we can do about that. But then, in a year's time, when you're doing some research and this stuff comes up, you kind of go, oh yeah, I remember that, and you actually find that you understood a bit more than you maybe thought you did at the time. That's for hope. Just gonna knock on. I'll be back in a second.
Yeah. Mm-hmm.
What can I rub off?
In the middle, everything,
Okay.
but not right and left.
Okay.
happy?
Yeah, this one, yeah.
Okay.
I'll just write that.
Yeah.
Okay.
Good.
Yeah, thank you.
So what else did you look at?
So I can.
You said you thought you did one of the exercises.
I did 4. Yeah, exercise 4.
Okay,
I
shall
hope
shall I have
so.
a look at what you did?
Like 21, 4.
Okay. Every sequence of points of A, B has a subsequence which converges to a point. Okay.
So here.
Mm. Yeah. Okay. So how do you know that the limit is between A and B?
This one from a theory here.
Okay.
Mm. Oh, yeah, this one.
Da-da-da. Yeah.
But
Oh yeah.
if it
We
is
went through
between
that. Yeah.
this,
Yeah.
yeah.
Okay. Okay. That's good. Yeah. Yeah. Exactly. Yeah. So that's all there is to it.
Can we do then the frame exercise 3? I couldn't. Oh, what is it? Page. No, this one. What is it? Exercise. This one here.
Okay. I don't remember this one. Wait. So where was it? Just tell me the number again of the.
Page 46, 3, 5, 6.
Yeah.
Sorry,
Yeah. I've got it.
exercise
I've got
5,
it.
7.
Yeah. Yeah. Okay. K greater than I.
So we haven't actually seen any examples of these sequences defined inductively. So,
Okay.
so maybe that doesn't help. This is something you get all the time in economics, right? You know, do you remember an AR1 process?
Oh yeah.
Yeah, so this is kind of sequence defined inductively. Macroeconomics is
Or
full of
econometrics, I think. No?
yeah, econometrics, but macro as well is full of things like that. So you know, implicitly there's some induction going on in the background.
One of the sequences x2n and x2n minus 1 is increasing and the other decreasing. Prove that both sequences converge to a limit L, which is positive.
So this is a bit of an introduction to the theory. So this is called a recurrence relationship, this kind of equation. So
How
it's
is it called?
a recurrence relationship,
okay.
specifying tomorrow's thing as a function of today's. And macro you get them a lot, okay? And in the macro lectures you'll see general tools for solving the limits of recurrence relations. This is a particular one.
Did it show that one of the sequences x2n,
So let me write things down. So we've got xn plus 1 is k over 1 plus xn, the funny sequence.
and they want us to look at x2n and x2n minus 1.
So x2 so x2n is x on the even values, right? So it makes sense to start by looking at xn plus 2. Okay, if we know xn plus 2 is a function of xn, then that's how you get from one even point to another even point. Okay, so maybe that will tell us something. So xn plus 2 is k over 1 plus xn plus 1. That's just for definition. Okay, now let's plug in for xn plus 1. This is something you'll do a lot in macro and time series econometrics. Plus k over 1 plus xn. So all we've done is just plugged in there for definition. Okay, that's easy. So let's simplify a bit. We've got 1 plus xn on the bottom. It's a bit of a mess. Let's times top and bottom by 1 plus xn. So we have k times 1 plus xn divided by 1 plus xn plus k. Okay. Oh no, actually, sorry. Ignore that. Let's not simplify. So the claim was that one of the sequences x2n was increasing and the other was decreasing, and we know that x1 is positive. So if x1 is positive, then I don't know. Maybe we should have done that. It's not obvious to me. What did I say? 1 plus xn plus k. So let's just try something. Okay, let's just get some feel about how it works. So let's suppose that k equals 1, and let's suppose that x1 is equal to 1. Okay, then we know that x3 is equal to 1 times 1 plus 1 divided by 1 plus 1 plus 1. Just plug in numbers there. So this is 2 divided by 3, so this is 2/3. Then we have x5 is 1 times 1 plus 2/3 divided by 1 plus 2/3 plus 1. So this is what we've got 5/3 on the top. We've got 2, 3, 6, 8/3 on the bottom. Okay, so this is 5/8. So it does seem to be getting smaller, doesn't it? So it looks like the odds are decreasing and the evens. So
okay.
but we haven't proven anything yet. That's just kind of given as an indication.
Yeah.
So let's see if we can do it a bit more formally. So what we want to prove is that it's kind of funny. Does it say anything about the size of x1? No, that's just positive. So if x1, let's just plug. What would x2 be? So x2 would be 1 divided by 1 plus 1. So x2 would be a half.
But why k is 1?
Well, I was just taking a value to see what happens.
Okay.
So I guess there's going to says they're both going to converge, prove that both sequences converge to the limit L. So what we know is that the odd was decreasing, right? Okay, the even is increasing. So and they're both converging to some limit. So this, let me draw a limit as a dotted line. So it must be something like that. Okay, so that's, if the question's right, that's what the picture must look like. These are the odd values decreasing, these are the even values increasing. So there must be some point, L, so if x is bigger than L, then xn plus 2 must be smaller, and if x is less than L, then xn plus 2 must be bigger. Okay, so we want to find the point at which xn plus, so there must be some point in the middle where they're equal.
Yeah.
Yeah. So one way to find where that point is, well, at that point, if x is at that point, then
Do they have to be exactly equal or just very, very small that they tend to the same limit?
so these two things are tending to the same. Yeah, but they'll never be exactly equal.
Okay, yeah.
But we can solve for what must happen, what they must tend to, because the point they must tend to should satisfy x is k over 1 plus x. You know, if they're at that point, then tomorrow they will also still be at that point. So this, if you like, is the stable point. Okay, once you're at that point, you never leave it. So this point is x times 1 plus x is equal to k. So this is x plus x squared is equal to k.
So we have to prove that as well.
So
No, yeah.
yeah, prove. Okay, so that's why this is the obvious guess for what the limit would be. Okay, because it's the point. If you're at that point, so suppose xn xn is the root of this. Okay, so xn equals k over 1 plus xn. Suppose that was true. Then, well, what's xn plus 1? Xn plus 1 is k over 1 plus xn by the definition of xn plus 1. But this is just the definition of xn. Okay, so if xn satisfied this equation, then xn plus 1 would be equal to xn. So once you're at that point, you stay at that point forever. Okay, so that's why it's natural to look at. It's going to be useful for us to find this point, because we think if it's above the point, it's going to be decreasing. If it's below, it's going to be increasing. So what's the solution to this quadratic? It's a long time since I've done this for a problem line. Have you seen this way of solving quadratics?
But it's interesting.
You know, it's not nice to always just, it's not nice to plug things into a formula. And, when you're working with the properties of normal distributions, this method, it's called completing the square. This is something that you use. So, what have we done? Well, we know that x plus a half squared is going to give you x squared, which is that term. It's going to give you 2 times this times that, which is going to give us that. Okay, and then it's going to give us a constant term, which is a quarter.
Yeah.
But we don't like that constant, so let's just subtract it off afterwards. Okay, so x plus a half squared is equal to k minus a quarter. Okay, so x plus a half is equal to plus or minus the square root of k minus a quarter. So x is equal to minus a half plus or minus square root k minus a quarter. we think that x is always positive. X started out positive, so we think it's probably always going to be positive. So let's make the guess, but it's the positive solution. Okay, so this is going to be the positive solution. So let's call this x star. Okay, so we're just defining x star as this thing. So let me write it up. X star equals half k square root k minus a quarter. Oh, wait, what have I done? I've missed the sign somewhere, haven't I? This was minus a half plus. Yeah, that's what I meant. Minus a half plus. Yeah, that's right, isn't it? Okay, so this is just, we're just defining that. Can I write this out?
No, before you do that,
Okay.
why you started from there? Because we wanted to prove that one is decreasing, the other is increasing, right?
Yeah,
we went by indication, just using numbers, and we found it.
yeah.
But then you jumped here.
Because, so we're going to want to prove an inequality about xn plus 2 in relation to xn. But we know that the behaviour is going to be different if it's above the limit or if it's below the limit. So what we're going to want to do is we're going to show that xn plus 2, we're going to show that if xn bigger than x star, we're going to show that that implies xn plus 2, so if it's bigger than it is less than xn. Okay, so we want to prove that, and we want to prove that xn less than x star implies xn plus 2 greater than xn.
Okay.
Does that make sense? So you have to think a few moves ahead. It's a bit like chess.
Yeah. Okay.
Okay, can I rub this stuff out?
Yeah.
Okay. So let's try and prove this. Okay, so if xn is bigger than x star, we have xn is bigger than minus a half plus square root k minus a quarter. Okay, so xn plus a half is bigger than square root k minus a quarter, kind of working backwards. So So what we want to do is we want to prove something about the xn, about this thing, xn plus 2. Okay, this bit there doesn't help, I think. So if xn is greater than this, we want to try and get to this expression. So 1 plus xn is greater than a half plus square root k minus a quarter. Okay, I've just added 1 to both sides. So 1 divided by 1 plus xn is less than 1 divided by half plus square root k minus a quarter. And then we can multiply both sides by k, so k is...
Okay.
I hope this is going to work. So, and then we can add but 1 to both sides. Everything's been positive, so we haven't done anything wrong so far. K over 10 plus 1 plus so remember, final step, we want to do k divided by all of this. Okay, so I'm just going to put it in here because I'm running out of space. So k divided by, well, no, that's a mess, isn't it? Sorry. Let me write over here. So k divided by 1 plus k over 1 plus xn, well, that must be greater than k divided by 1 plus k divided by half plus k minus a quarter. Okay, so what we have on the left hand side now is xn plus 2. Okay, let's just call this xn plus 2. Kind of lost me. Sorry, I don't think this is going to work. Let me just try something quick. So xn plus 2 minus xn, well that's k over 1 plus k over 1 plus xn minus xn, which is k 1 plus xn divided by 1 plus xn plus k minus xn times 1 plus xn plus k divided by 1 plus xn plus k. Which is, so we've got a kxn term which cancels. That's the only term that cancels. We've got 1 plus xn plus k. So we get k minus xn minus xn squared. Yeah, this is easier, isn't it? I'm afraid it's impossible to do maths without occasionally going in completely the wrong direction. So here we have, this is just xn plus 2 minus xn, and we've got it down to this thing. This thing on the bottom is positive. Okay, so xn plus 2 minus xn is greater than 0 if and only if k minus xn squared is greater than 0.
Yeah.
Which is true if and only if k is greater than where were we? Xn plus xn squared. And this is a quadratic, right? So quadratic is going to look something like that. It's got a positive solution. What we're saying is that sorry. This is clearer, isn't it? So this quadratic is the quadratic we had before, right? It's just
Yeah,
the same. Okay, so, but it looks something like that, doesn't it? It's decreasing because we've got a minus xn squared term. Okay, we know this point here is x star. We know what x star is. So we say we want this to be bigger than naught. Okay, so that means that xn has to be in this interval
Yes, between 0
and
yeah.
x star. Okay, so this is if and only if naught is, if and only if xn is less than x star.
Okay.
Okay, so what have we proved? We've proven xn plus 2 is bigger than xn if and only if xn is less than x star, which is what we wanted. So if you're bigger, if you're less than x star, then you're bigger, you're increasing. If you're bigger than x star, then you're decreasing.
Okay.
Okay, so we got there in the end.
Mm.
I should have tried this to start with. It was an obvious thing to do, taking the difference between the things. You know, so we wanted to know whether xn plus 2 was bigger or smaller than xn. So looking at the difference between the two was the obvious
Yeah,
thing
but
to do.
here why it takes x to n minus 1 and we
Well, so we've done that. So x2n is all of the even terms. x2n minus 1 is all of the odd terms.
Okay, so
So we're
instead
looking-
of writing it, yeah. Okay.
Yeah, so we're looking at kind of going up by 2 steps each time. Okay, so if you start above, so the first element is above. Okay, so that gives you, so the one of them will be decreasing, one of them will be increasing.
Okay.
So okay, so how do we prove that they have to converge to something? Well, they're bounded. Right, the odd elements are all above x star. The even elements are all below x star. So they're bounded. They're decreasing. Thus, they must converge to their supremum or infimum, respectively. So the supremum is, yeah, the supremum is just x star in both cases. So you basically done at that point. Conclusion may be drawn concerning xn. Okay, so by the sandwich theorem, xn converges to the same limit.
What's the conclusion?
That xn converges to the same limit. So you can sandwich xn between that sequence and that sequence. So it must,
Okay.
or you don't even need that. If a subsequence converges to a limit and xn converges, then xn must converge to the same limit.
Okay, yeah.
Okay. Did you try any other exercises?
I think this is what we had, right?
There were a few from the last page, I think. From these series you didn't do.
Yeah, maybe for tomorrow. Yeah.
Okay.
Yeah, because you didn't say anything about series.
Did I? Oh, we didn't. No, we didn't get that far, did we?
Yeah.
We didn't do many. Didn't I say a few more? Didn't I say 5 and 6 here?
So we did 1, 4, yes, 6, not 5, 6.
Well, it's fine. Don't. Well, you won't be. If you do 6, you need to do 5 as well, I think. But don't worry about it. You've worked enough. I would take the evening off.